Welcome to lesson 2.7. In this lesson, we're going to look at graphs and we're going to make sure we can graph the different types of families of equations. So we've talked about number lines, and number lines is actually your horizontal or x-axis. And then once we put in the y-axis, this is called a coordinate plane. So x goes side to side, y goes up and down, and then 0, 0 is what we call the origin. That's the center of your coordinate plane. We want to be able to plot points. So we have some examples. Let's look at number 1. Remember, up and down is your y, side to side is x, and our ordered pair always has x comma y, so side to side first, and then up and down next. So if we look at -1, 2, I go side to side, so -1, and 2 is positive, so I'll go up 2, and that'll be my -1, 2 spot. Now if I want to look at 4 and -2, 4 is the x, and then -2 is my y. So it'll be 4 and -2. So you want to keep remembering x, then y. So let's look at how to apply this. One way to apply it is when you're looking at change, relative change or absolute change. So those are the keywords we want to make sure we are looking for. And then percent change that we mentioned earlier. So absolute change is where we just subtract the two. So I'm going to take the new population, so the more recent one, subtract the old. So in my calculator or on paper, 6.7 million minus 5.9 million. Then relative change would be subtracting those two answers, but then dividing it by the original population amount. So that case will be the 5.9 million. And then because it wants a percent, that tells me I'm going to need to multiply 100 and then make sure we round to the decimal if needed. And then we're going to use our graphing skills to further apply that. So we want to be able to match graphs to possible scenarios. This graph is a line, linear, and it's so when we have linear, that means it's a constant change. So nothing crazy is happening. There's no dip, no peak. It's not a curve. So that's how I know it's a constant rate. This is why it's linear. This one we have a curve, so it kind of starts to grow fast first and then kind of tapers off. Here it looks like there's some kind of event that decreases the population immensely. So it could be a weather, or it could be famine, it could be maybe taxes go up and everyone wants to vacate the state, so lots of possibilities, but something happened to make the population decrease. And then opposite of that, there's another event, but this time the population's increasing. So maybe they got rid of some kind of tax, or maybe something became legal that other states weren't making legal. So this would be a positive event, or something that makes population increase. And then it asks you to apply those absolute changes. So let's look back at what the absolute and the relative change were, and then we'll be able to apply it moving forward. So the absolute change was 800,000, and then the relative change was 13.6%. So in 2010, we had 6.7 million. So then we would just add 800,000 to that to figure out what the 2020 population would be. That's our constant change. Now, if it's a relative change, we would take that 6.7 million and multiply it by 1 plus that relative change, or that percent change. And when I plug it in the calculator, I get 7,611,200. So these absolute and relative changes actually have to do with different types of graphs. So constant is linear, like I said. We have also quadratic and exponential graphs. These are called families of equations. So we need to know 3 different types of families, and those are the linear, exponential, and quadratic equations or families. One great way to tell which family an equation belongs to is by their exponent. So if we have x squared, it's going to be quadratic. So anytime the exponent is 2, that's going to be a quadratic. If the exponent is the variable, that's exponential. And then if there are no variables, no powers, then it's linear. So these are the key differences that we'll need to remember for the rest of the modules. Once we can identify the family, we can figure out which graph. So linear equations are going to produce straight lines, and it's either going to be going up if it's positive or going down if it's a negative slope. We'll talk about slope later. Exponential equations have this J shape, and it's either going to be a growth, so if it's going up, that's a growth, or a decay, and that's if it's going down. That's kind of like the negative. You'll notice the difference is the base. And then the last one is the quadratic. So quadratic produce a U shape. So here we have the U shapes. And if it's pointing, both arrows are pointing up, that would be positive. And then if it's pointing down, that would be negative. So one way to graph is using tables. Tables are a great way to start graphing if you're not familiar with formulas. Another way is to use slope-intercept form if you're dealing with linear equations. So let's look at one of each type. This one is linear. I know that because there are no powers. And we're being requested to use a table in order to graph this. So 0 is a great number to plug in. So I'm going to say y equals negative 5/2 of 0 plus 1. Well, I know that gives me 0, so then I end up with 1. Then if I plug in 2, y equals 5/2 of 2, and then plus 1. So the reason we pick 2 is because it can cancel out easy. So then I get negative 5 plus 1, so that's negative 4. And we want to pick the opposite of that, right? So instead of a positive 2, let's pick a negative 2. So negative 5/2 of negative 2 this time. 2's cancel, and this time the negatives also cancel. So I get 5 plus 1, which is 6. And you do the same thing for the other two. So once we get the rest of the table values, we can start to plug in our ordered pairs. So 0, 1, 2, negative 4, and then 2, positive 6. So 6 is going to be off the graph, so I really can't graph that. But on the computer, you only need 2 points that are on the line. So here we have exponential. I know it's exponential because that x is in the exponent. Now it's telling me to round to 3 places if I need to. Let's go ahead and plug in some of these numbers. If I plug in 1/2 to the 0 power, anything to the 0 power is 1. And then let's plug in 1. So that'll give me half, or 0.5. And then if I plug in negative 1, we can invert it, so it actually gives me 2. So when I'm graphing these, 0 and 1, then I have 1 and 0.5, and negative 1 and 2. If we plug in our 3's, we actually see that it gets close to this x-axis, but it never touches it. And the last one we're going to look at is this quadratic. I know it's a quadratic because my exponent is a 2. So if I'm plugging in values, I'll start with the 0. Notice 0 is in all of these. That's because it's the quickest to plug in. All right, 0 to anything is going to be 0. So I get negative 4. If I plug in a 1, I get 3 times 1, which is 3. And then that equals negative 1. So then let's plug in negative 1. I actually get the same answer. So that's one thing about quadratics is they mirror each other. So whatever I get for the positive, that's going to be my answer for the negative. So 3 times 2 squared, that gives me 3 times 4, which is 8. So then the negative 2 should give me 8 as well. When I plot these, let's see, 0 and 4, 1 and, oh, that's why it should be negative 4. And then 1 and negative 1, negative 1 and negative 1, and then 8 and 8. And I can't plot those, but it's going to be kind of this curved V shape.